Okay, this question, a particle A of mass 3m, a particle B of mass m are moving along the straight line on the smooth horizontal surface, opposite directions, and it gives you the speed after, and the speed of A is v, and speed of B is 2v. So I've just changed that into a diagram, and given the magnitude of the impulse, and we asked to find v in terms of u only. So what I've done there, I've done the impulse equation, and I've cancelled the m's, rearranged it, and I got v is equal to a quarter u. Part B, find two possible values of k. So what I've done there is I've done the conservation of linear momentum equation, and I've substituted for v and rearranged it. I think, yeah, I've rearranged it, and I've worked out what k is. K came to 3/4, and then I've said, well, that's if the two particles move in the same direction. But if they're moving in the opposite direction, so I've done the linear momentum again, and I've simplified it and substituted in the value for v, rearranged it, and I got, that was after cancelling the u's, because there's a u in every term. I got k is equal to a quarter. So it was, I think, 3/4 or a quarter. There's all that information there. So I've redrawn the diagram, putting in everything that was given, and we're asked to work out the tension. So I've done an equation of motion. There's an acceleration. So the equation of motion is the driving force, take away the sum of the two resistances, 100 and 200, take away the parallel components of the two weights of the van and the trailer, simplified it, and I got A is equal to that. And then I've just looked at the trailer by itself. This time the tension is the driving force, just looking at the trailer, and you take away the parallel component of the weight and the resistance, and I rearranged it, and I got tension is equal to 307 newtons to three significant figures. This question, so a particle P of mass 0.5 kilograms moving in a straight line with that speed, and it receives an impulse of that much. The angle is alpha, and we're given the tan of alpha is 4/3, and we're asked to work out the speed immediately after the impulse. So what I've done there is I've done the impulse equation. Now, impulse has to be in line with the actual the path of the particle, and I've done 3 cos alpha is equal to the mv take away mu, which I've just factorized, took out the 0.5, and the other way, 3 sine alpha is equal to the same, and because it's just moving horizontally, the vertical u is 0. So then I've taken the top line. Remember, cos alpha is going to be 3/5 because tan alpha was 4/3, and simplified it, and then done the bottom line, and I got v is equal to 4.8, and the speed I've just worked out by doing that Pythagoras calculation. For this question, you got all that information. We're asked to work out the size of the angle through which the direction of motion of A is turned as a result of the collision. So I redrew the diagram and I put in theta there. Now theta is the angle from the horizontal to the path of A as it moves away. I've written the that's the conservation of linear momentum equation. Simplified it. Cos 30 was √3/2, remember, and cos 60 was a half. Simplified it and simplified it further, and I got that equation there. And then I've done a perpendicular to the line of the collision, where just the components, in this case the vertical, because the line of collision is horizontal, those components are going to be equal. And then I've done the same for a B, and I got that in terms of U, because I knew the angle that was coming off. I didn't know the angle. I don't know what theta is, but I do know from the diagram that it's coming off at 60. So coming in at 30 and leaving at 60 for B, and I got that. Substituted both A and B into equation 1, and you get that. And notice the whole objective was to get it all in terms of U, and then you can cancel the U's. So that's where I ended up in that last slide. And I'm going to get it all on one line by multiplying through by 2 √3 tan theta. That will cancel all the denominators, and you get that. You just rearrange that and do tan to the -1. You get theta is equal to 72.2. Now, that isn't the angle of deflection. Now, remember, the angle of deflection is the angle that it turns from, if it carried on in a straight line, to the path it's taken now, that angle. So I was going to have to do 180, take away that 72.2, take away that 30. That gives me that angle of deflection of A. Part 2, it says find in terms of M and U the magnitude of the impulse received by B in the collision. So I did the impulse equation for B. Impulse, remember, it acts in line of the in line with the collision, the dotted line. So we're going to take the components of the velocity in line with that, and put in everything I knew, simplified it. What have I done there? I've rationalized the denominator for that part, and added them, and I got that. Yeah, that's in terms of M and U. This one, I put in all the information. I wrote drew the diagrams for it, and I did the conservation of momentum. I cancelled the M's and simplified it. And then I did Newton's equation. Now I put P and Q moving in the same direction, so it's going to be the relative velocity is Q minus the P over 3U, and rearrange that. Equation 1 was that rearranged, and so what I did, I got equation 2, multiplied it by 3 to get that 3 in front of the P, and I added them, and I ended up with that divided through by 7. In that, there's in the question, it should say 9e plus 2. The e is missing from the 9, but that what I've just written there is the correct answer. Then it rebounds, the collision rebounds perpendicular to the coefficient between the wall is a half. Find the complete range of values of E for there to be a second collision. Right. So it comes out hitting the wall with that, what we just worked out, and going back is going to be a half that, because the coefficient of restitution is a half. So coming after hitting the wall, it's coming off at that U over 14 times by 2 plus 9e in brackets. And I've done the Newton's equation there from before, and what I've done there is I've substituted, I multiplied by 3u and substituted for q, and p was equal to that. Now, if p is moving in the opposite direction to my first diagram, okay, so it's hit, the two particles have collided, and instead of P moving in the same direction towards the wall, we're going to say P is safe, it's moving in the opposite direction. So it kind of, it collides and kind of rebounds away from the wall. So for the collision to happen, Q, all right, after it's hit the wall, has to have a speed bigger than the speed of P, okay, which is moving away. Okay, so it's going to catch up with it and collide again. And I've got that. I cancelled the u's and multiplied by 3 by 14 to get rid of the denominator, and cancel the u divided by u. And I ended up with that. And simplified it, and I got E has to be less than 2/5. If P was carrying on moving in the same direction, then there was bound to be a collision. So the extreme case is if P is moving away, is Q going to catch up with it? So for it to catch up and collide again, E has to be less than 2/5. Remember, E is between 0 and 1. So if it's less than 2/5, it has to be greater than 0, but less than 2/5. Right, this question, you're given a lot of information. So I've put in all the forces, and it says find the potential energy lost by the whole system as a result of B falling 3 meters. So the gravitational potential energy lost by P is going to be 4 times G times 3. Take away 2G times by, A has risen, but we want how much it's risen vertically. So it's going to be 3, because B has fallen 3 meters, so A has gone up by 3 meters. So we don't want the 3, we want the sine of it, so 3 times the sine to work out the vertical, how much it's moved up by. Oops, and it came to 82.32. B, it says use the work energy principle to work out mu. Mu is the coefficient of friction, and it says given that B at the instant hits the ground is 4.5. Right, so I've said just the change in gravitational potential energy, because this thing is released, so the energy at the beginning, right, before it sets off, is just the gravitational potential energy. So the change in gravitational potential energy is equal to now that all that is converted to the kinetic energy of A plus the kinetic, it's the whole thing acts as one entity, one thing. So the kinetic energy of A plus the kinetic energy of B plus any work done against friction. So I've already worked out the change in gravitational potential energy. That's the potential energy lost that is converted, okay? And I've put in all the figures for that, kinetic energy, and plus the work done against friction. Now, the work done against friction is the actual friction times by the distance. That 15.68, the working of which I haven't included, is the reaction. That's going to be 2G times by the cos of theta, like how we normally find the reaction. The cos of theta is going to be 4/5, so it's 2 times 9.8 times 4/5 times by the distance it's moved. So when you rearrange that, simplify it, you get mu is equal to 0.46. Right, then it says B hits the ground, A continues to move up the plane but does not reach the pulley in the subsequent motion. Block A comes to instantaneous rest after moving a distance of 3 plus D. So what I've done there is for A, right, after it's moved 3 meters already, the kinetic energy afterwards, okay? So let's say all that's happened, it's moved 3 meters, okay? What's going to happen next is going to carry on moving a distance of D, and then that's going to be equal to for just A, that kinetic energy is going to be converted to the gravitational potential energy plus the work done, right, by moving from where it finished after the 3 meters to D, the distance moved D. So I've put that in. Half times mass 2 times by the velocity. Remember, it's going to come to instantaneous rest. Okay, so all that kinetic energy is just going to vanish. It's going to just go. So all that came to 20.25 is equal to the mass times mg times by d, and we want the sine times that by the sine to work out the vertical displacement. Plus, now we know what the mu is now. So the reaction times by mu times by d. And I simplified it and I got worked out d as 1.07 meters. Okay, this question, I just put in the information there. So the natural length is A, extension is 2A. So the total distance is 3A. Now it says somewhere there, AB is 3A at the end of that first paragraph. So I split that into A and 2A. And what it says is after being released from B, package P comes to instantaneous rest at A. So it goes all the way to the top. So it goes past the natural length, all the way up to right to the top. And by modeling as a spring being light and modeling P as a particle, show that the modulus of elasticity is 2 mg. So I've said the elastic potential energy lost. Now the elastic potential energy it's got is lambda times x squared, the extension squared, over 2a, 2 times the natural length at the bottom. The gravitational potential energy gained, well, it's gone all the way to the top, so it's gained mg times 3a. And now the elastic potential energy gained is lambda over 2a, right, times by the extension squared. Now remember, extension doesn't necessarily have to be extended. It could, the spring could be squashed. Okay, it's the same formula. So it's gone, even though the natural length is a, it's gone past the natural length, right? So the extension is still a, but into the actual spring. So I've simplified it and I've got lambda is equal to 2 mg, what they asked for. All right, B part 1, show that P attains a maximum speed when the extension of the spring is half a. So I've said the maximum speed is when the acceleration is a 0. So using F equals ma, so there the driving force is the T, and the resistive force is the weight, and there's at the point of maximum speed, the acceleration goes to 0. So I made that equal to 0, substituted the lambda, the x for the extension, and a natural length a, take away mg. Simplified it, cancel the g's, cancel the m's, and I got x is equal to a over 2, or a half a. Part 2, B part 2, it says use the principle of conservation of mechanical energy to find the maximum speed, giving your answer in terms of A and G. So I've got that as so at the start it's just elastic potential energy, right? It's extended to a, so it's x squared, so it's 2a squared. So what I've done there is, you know, where after the natural length, I've put that, I've referenced that as a 0 point. Okay, so that's like, you know, where the extension is 0. So so that initial elastic potential energy, what it's the only thing it's got at the start, has been converted to the gravitational potential energy gained, which is mg times by 2/3 of A. Now, sorry, not 2/3, 3/2, 3/2. Now, if it's moved up by a half A, then no, sorry, if the extension from the reference 0 point is a half A, it's actually moved up 1.5 A. Okay, so from the natural length, the extension for the maximum velocity is a half A. All right, the whole extension was 2A. So 2 take away a half is 3/2, 1.5. So it's gained, that's how much it's moved up, is equal to the elastic potential energy at that point. Now the elastic potential energy is A/2 squared times by lambda over 2A. Remember, if it's moved up 1.5, that means it's still extended a half A. So it's half A/2 squared plus the kinetic energy at that time. So what I've done there is I've just simplified it carefully. There's no point making a mistake there. Just take your time with that, something that's looks complicated like that. And then I've cancelled the m's and divided through, well, I've just rearranged it. I got v is equal to that. Part C, state one way in which this would affect your energy. In reality, the spring is not light. One way in which it would affect the energy, if the spring has a mass, then the spring's gravitational potential energy would have been included as well, because that would have to have a mass as well. So the mass times g times the extension, the mass of the spring, that is. Right, for this, I've only done part A for this. Find the full range. So doing a diagram there, putting in the vectors like in column form, and it says find the possible values of E. Now, for that to hit the wall ST, that angle or that gradient of the path, the PQ path, has to be less than the gradient of the wall. If it's parallel to it, or the gradient is bigger, it's not going to actually hit the wall. That's common sense. Okay, so I've said E is equal to Q over 8. Okay, remember the top line is like along in this parallel to the first wall, and the bottom one is the perpendicular to it. Now Newton's law is only applies to perpendicular, so it's Q over the path, the speed of approach at the bottom, speed of separation at the top. So I've got Q is equal to 8E. P horizontally, remember this is all in components, so we don't have to worry about cos and sine and so forth. So P is equal to 6 because it's already split into components. So I've said for impact with ST, the gradient of the ball, or is it a ball? Yeah, a ball. For impact, the gradient of the ball has to be less than the gradient of ST. So I've said 8E, which I've just worked out, over 6. And I've simplified that 4E over 3. That gradient has to be less than a half. Now, where did I get the half from? Well, in the second sentence, it says ST is in the direction of 2I. So 2 to the right and 1 up. So that gives a gradient of a half. And I've said E, just simplified that, rearranged the 8E has to be less than 3. E has to be less than 3 over 8. And because E is between 0 and 1, if it's less than 3 over 8, it can't go beyond 0. So E is between 0 and 3/8. Okay.